Okay, let's unpack this. Today, we're diving deep into gravity. The force that's absolutely everywhere, but still one of the most baffling things in physics.
Right. It keeps our feet on the ground, sure, but
Okay.
it's also this huge cosmic sculptor. Shapes galaxies, creates these, well, extreme objects.
Our mission here is to sort of boil down a whole stack of material, stuff that covers gravity from, its first mathematical steps way back, right up to the edge of astrophysics today.
Exactly. We're talking about the force that runs everything from planets orbiting to how they even formed in the first place. It spans all scales.
Yeah, and we've got these great instructional summaries, some specialized bits too, really clear stuff designed to get to the core ideas.
Mm.
And we should definitely give a nod to the work behind these sources, especially the effort by physics teacher Veli Torun in putting this information together and sharing it really helps lay it all out.
That's a great foundation. And if you think about the big picture, we're essentially tracking gravity through, say, four main ideas. First, the basic universal law. Then, how it gets a bit weird right here on Earth. Then what happens if you go inside the Earth. And finally, the absolute extreme, black holes.
Right, let's start with the foundation then. Newton's law of universal gravitation. This isn't just like things falling down.
No, it's more fundamental. It's about this mutual pull between any two things that have mass. Newton basically gave us the rule book for it.
And he said, the force depends on two key things: how much stuff mass there is and how far apart that stuff is.
Yeah, the mass part feels pretty intuitive. More mass, like a huge planet versus, I don't know, a pebble, means a stronger pull. Simple enough.
But the distance part, that's where the real kicker is, isn't it?
That's the genius of it, absolutely. And where all the predictive power comes from. It's the inverse square law.
Ah, yes, the inverse square law. Sounds simple, but unpack that a bit.
Well, it just means if you double the distance between two things, the gravity between them doesn't just get cut in half. It drops by 4 times. So double the distance, 1/4 the force. Triple the distance, it's only 1/9 as strong.
Wow, okay, so it falls off really fast.
Super fast, which is why, gravity feels relatively weak in our day-to-day lives, even though it's running the whole cosmic show.
That rapid drop-off,
Yeah.
that must have huge consequences out in space. What did this predictability actually let us figure out?
It basically told us the universe operates on understandable rules, like a giant clockwork almost. And the best proof, probably the discovery of Neptune back in the 1840s.
Right. The planet found purely with math, the ultimate aha moment for physics.
Pretty much. Astronomers saw that Uranus wasn't quite following the path Newton's law predicted. It was speeding up sometimes, slowing down others, just slightly off.
A wobble?
Exactly. And they figured, well, if the law is right, something else must be out there unseen pulling on Uranus gravitationally, a disturbance, a perturbation.
So they used the law to look for it.
2 scientists, Adams and Leverrier, independently crunched the numbers. They used the inverse square law, Uranus's mass, its weird movements, and calculated that there must be another planet, how massive it should be, and roughly where to look for it.
They literally calculated a whole new world into existence just from a slight wobble. Incredible.
And sure enough, astronomers pointed their telescopes where the math said to look, and bang, there was Neptune.
Wow.
It was huge confirmation. Gravity isn't just local, it links everything everywhere. And that same inverse square law, that rapid fall off. It's why a planet like Mars struggled to hold onto a thick atmosphere like Earth.
How so?
While Mars is, about 50% farther from the sun than Earth? That might not sound enormous, but because gravity weakens with the square of the distance, that difference was enough to significantly weaken the sun's gravitational hold on Mars's early atmosphere, letting more of it escape into space compared to Earth.
So the same math explains planetary orbits and why Mars is, well, the way it is today. Amazing. Okay, let's bring it back home. Down to Earth. We all learned that gravity, little g, is 9.8 meters per second squared. Like it's this fixed number.
Right, the standard textbook value.
But our sources are pretty clear. It's not actually constant everywhere on Earth. What are the main reasons for that variation? What stands out?
The big takeaway is that 9.8 is just an average, a very useful average, but still an average. Gravity definitely varies, and there are 2 main culprits.
Okay, what's the first?
First is the Earth's shape and its spin. See, the Earth isn't a perfect sphere because it rotates, it bulges out a bit around the middle at the equator.
Ah, so it's slightly flattened at the poles and wider at the equator, like a squash ball.
Exactly. So if you're standing on the equator, you're actually physically farther from the Earth's center of mass than if you were standing at one of the poles.
And because gravity depends so much on distance, that inverse square thing again.
Precisely. That little bit of extra distance at the equator means the gravitational pull is slightly weaker there,
Okay, that makes sense.
and there's more. The spinning itself creates a centrifugal force, like being on a merry-go-round. That force pushes you outwards, slightly counteracting gravity, and it's strongest at the equator.
So two effects working together. Farther distance and an outward push.
Yep. Combine them, and the result is that gravity is measurably strongest at the poles and weakest at the equator.
That's fascinating. You actually weigh slightly less at the equator than at the pole. Most people wouldn't think about that.
Right.
What's the second main factor for gravity variations?
The second one is more local. It's about what's directly beneath your feet. The local geology, the topography.
Meaning mountains and valleys?
Yeah, partly. Gravity decreases slightly as you go up in altitude, say, climbing a tall mountain. That's expected. You're farther from the center. But it gets even more specific. If you're standing over a deep ocean trench, there's literally less dense mass directly below you pulling you down compared to being over solid trust. So gravity is a tiny bit weaker.
And the opposite is true too.
Absolutely. Stand over a really dense deposit of minerals, like a huge chunk of iron ore underground. Gravity will be fractionally stronger right there because there's more mass concentrated beneath you.
So wait, people actually use this. They measure these tiny gravity changes.
Oh, definitely. Geologists use incredibly sensitive instruments called gravimeters. They map these micro variations in gravity to look for things underground.
Like finding minerals or oil.
Exactly. Dense ore bodies, petroleum reservoirs, even tracking changes in underground water levels, it all affects the local mass distribution and, therefore, the local gravity. Shows how sensitive the force is.
Okay, that's gravity varying across the surface. Let's push this variation idea further. Let's go inward.
Ah, the classic thought experiment.
Yeah. If we could somehow drill a tunnel straight through the Earth, right through the core and out the other side, ignoring the heat and pressure, obviously what happens to the force of gravity on you as you fall from the surface down towards the center.
Right. This really gets you thinking. So at the surface, the whole planet is below you, pulling you down.
Makes sense.
But as you start falling into the Earth, things change. The key idea here is that only the mass that's closer to the center than you are still pulls you inwards.
Hold on. What about all the mass you've already passed, the layers now above you, or sort of surrounding you? Doesn't that pull you back up towards the surface?
That's the counterintuitive part. But no, it doesn't. There's this principle. Newton figured it out too, sometimes called the shell theorem.
Shell theorem.
Yeah. Imagine the part of the Earth that's farther from the center than you are as a big, hollow, spherical shell of rock and metal. The theorem says that the gravitational pull from that shell on anything inside it cancels out completely. The pull from the part of the shell nearest you is exactly balanced by the pull from the much larger but farther away part of the shell on the opposite side.
Wow. So as I fall deeper, more and more of Earth's mass becomes this shell around me.
Exactly. And that shell's gravity effectively disappears from the equation for you.
So the net inward pull gets weaker as I fall.
Precisely. The amount of mass actually pulling you towards the center decreases pretty much linearly as you get closer.
Okay, linearly. So what happens right at the very center?
Right at the exact geometric center of the Earth. Well, now the entire mass of the planet is in shells surrounding you equally in all directions.
So the pulls cancel out from everywhere.
Perfectly. The net gravitational force on you at the center is zero. You'd be completely weightless just for that instant you pass through the center.
Zero gravity.
Yeah.
Right at the heart of the planet.
Yeah.
That's wild.
Okay.
So if just changing position inside a planet can reduce gravity to zero, what happens when gravity just completely takes over, when it utterly wins?
Ah, well, that leads us out of the realm of planets and into the cosmic deep end. We're talking black holes.
Right.
And here, Newton's picture of gravity as just a force isn't quite enough. We need Einstein's view, general relativity, where gravity isn't a force, but a curvature, a warping of space-time itself.
The fabric of the universe getting bent. And black holes are where that bending goes off the charts. How do they form again?
It starts with a really, really massive star, much bigger than our sun. These stars burn through their nuclear fuel incredibly fast. That burning, the fusion, creates outward pressure that balances the inward crush of gravity for millions or billions of years.
But eventually the fuel runs out.
Exactly. When there's no more fuel for fusion, that outward pressure disappears, and there's nothing left to stop gravity. The star collapses inwards, catastrophically, under its own immense weight.
A total collapse.
A total collapse. The core gets crushed down, potentially to an infinitely dense point of singularity. And as the star shrinks, all its mass gets packed into a smaller and smaller space. The gravitational field at its surface gets stronger and stronger until it crosses a critical threshold. The gravitational pull becomes so strong that the speed you'd need to escape from its surface, the escape velocity, becomes faster than the speed of light.
And since nothing can travel faster than light.
Nothing can escape, not even light itself. That boundary, the point of no return, is what we call the event horizon.
Hence the name black hole. Light goes in, it doesn't come out. So they're just black.
Right. Now, this raises a really interesting question. When all that complex stuff in a giant star collapses down, what actually defines the black hole that's left behind? You might think, all the different elements, magnetic fields, complicated structures.
That maybe some of that complexity survives.
You might think so, but our sources point to something called the no-hair theorem, which is frankly amazing.
No-hair theorem, what does that mean?
It means that once the collapse is complete and things settle down, the resulting black hole is incredibly simple. It can be described completely by just 3 things.
Only 3. For something so extreme.
Just 3 external properties. Its total mass, its angular momentum, how fast it's spinning, and its overall electric charge, though usually they're expected to be pretty much neutral.
Mass, spin, and charge. That's it.
That's it. All the other details about what fell in the hair, metaphorically speaking, are lost, either radiated away during the collapse or just inaccessible inside the event horizon.
So gravity, in its most extreme form, actually erases complexity. That's profound.
It really is. And it ties back perfectly to Einstein's idea. The black hole isn't just a heavy thing. It's a place where space-time is warped so intensely, so deeply, that even light just follows the curve down into oblivion.
And they don't just sit there, right? They interact.
Oh, yeah. They aren't cosmic vacuum cleaners just sucking everything in randomly. But if gas and dust get close enough, they get pulled into orbit, forming these incredibly hot, fast-spinning structures called accretion disks around the black hole, and those we can see, often blazing across millions of light years.
So we've gone from Newton's neat inverse square law that let us find Neptune down into the Earth where gravity hits 0 at the core.
Right.
And then all the way out to these collapsing stars that literally break space-time. It really feels like the whole universe, for all its complexity, runs on just a few really powerful rules.
It does. And piecing together this journey from the foundations to the extremes was really helped by the clear way our source materials laid things out.
Absolutely.
Yeah.
And we want to circle back and again acknowledge the value of that clear compilation, especially the positive contributions from physics teacher Haki Velitoron. It really provided a solid framework for this whole discussion.
Definitely. So we've seen how sensitive gravity is to distance, to density, to how mass is arranged, which leads to a final thought, something for you to chew on.
Okay.
When a massive star starts that final collapse into a black hole, its total mass stays the same, right? It's just getting squeezed smaller and smaller.
Right. Mass is conserved.
So if you were, say, floating in a very heat-proof spaceship, a safe distance outside this collapsing star, what would happen to the gravitational force you feel pulling you towards it as it shrinks? Would that pull get stronger, weaker, or stay the same?
The mass is the same, but the distance to the surface is changing. Interesting question.
What does thinking about that make you curious to explore next about gravity, its basic nature, or maybe more about these cosmic extremes? Something to ponder.